Okay, we are interpreting graphs in this lesson. So basically looking at a graph and a graph that has an application with it and describing what it represents in real life. So first question says the amount of fuel left in a car's gas tank is related to the time during a driving trip. The graph consists of 6 line segments. Explain the significance of each one. So we don't have to do math and calculate rates per se, but we need to describe what is happening. So from A to B, so if you look on your graph, here's A and here's B. So what's happening there? Well, look at the scale. This represents 3 hours. Okay, so this is, we look at the actual coordinates, that's 340. So starts at 0. So it took the driver to 3 hours, and you need to look at the difference in the liters used. So started with 70 liters, ended up with 40. So they drove 3 hours and used 30 liters of gas. Okay. Then from B to C, you'll notice that the volume did not change. So that means basically they did not drive anywhere. So they were parked, and then for how long? You look from 3 hours to 4 hours. So that means for 1 hour they parked. Okay, they parked for 1 hour. Then C to D, so 40 liters in the tank at C. Here there are 10 liters in the tank. Notice how that line is purposely not right on the 7-hour line. So it's a little less than 7 hours. So that means they drove a little less than 3 hours and used up, so going from 40 to 10, they used up 30 liters of gas. So drove for a little less than 3 hours and used 30 liters of gas. D to E, so if you look at that, now the gas tank is getting filled up, right? So it's going from 10 liters to 70. So basically they're at the gas station and they're filling up their gas tank. So from D to E is, so they're stopped, right? So they're not using any gas. So basically stopped to fill up their gas tank, their tank to 70 liters. Okay, so back to what they had at the beginning. Then E to F, again using up gas because it's decreasing, so it went from 70 liters to 50 liters, and it looks like in 1 hour. So drove 1 hour and used 10 liters of gas. Now, in real life, do you use that much gas in 1 hour? Not in a regular vehicle, but we're just trying to use some kind of nice numbers. Maybe in a big truck or something like that, you would. And then from F to G, so notice how at that steepness of that line from E to F was is steeper than from F to G. So often when there's sort of an optimal speed that uses the least amount of gas. From E to F, they're not going at that. Okay, so they're going maybe at a really fast speed. Sometimes I think at a really slow speed will also use a lot of gas. But I'm not really an expert at that. So likely they're going pretty fast there. And then F to G, they're using gas at a slower rate. So that is for 2 hours, drove 2 hours and used, so here E to F, oh, actually, E to F is 70 to 50. That should be 20 liters. Okay, and then from F to G is 10 liters. Okay, and probably at a slower pace than E to F, so they're using the gas at a slower rate. Okay, so that's just describing. We didn't actually do any calculations to calculate the rate of volume use. We just described what was happening. Okay, next one, we're going to do the opposite. Given an explanation, we're going to draw a graph, or sketch a graph, really. Hikers Club went for a hike in a park. They traveled at a constant speed and stopped for a break. Then they then walked backwards towards their starting point at a slower pace than they started. Close to the end of the hike, they walked at a constant speed that was faster than their initial. Draw a graph that describes the distance the hikers are from their starting point over time. So this is important. It's distance from starting point. It's not the distance they traveled. So that means our graph will end up, because they're walking back home, back to the beginning, it will end up coming back towards starting point at the beginning here. Okay, so not there, it'll be over on the right. But if this was just distance traveled, then this graph would keep on going up and to the right. So you need to be careful and be specific about what you're drawing. So Hikers Club went for a hike in a park. They traveled at a constant speed. That means that we'll have a line segment, right? Distance over time. So remember, speed equals distance over time. And so that's going to be an oblique line, a diagonal line. And then they stop for a break. So you just choose, I'm going to draw my line here from the beginning, a line, whatever slope it is, okay, choose something. Not near the top. Well, you could go near the top. You could go a little higher, but not, make it a decent length there. Then they stop for a break. It doesn't say for how long, so we're not going to put a scale on this. So now I'm going to do another line where it's horizontal. They stop for a break. I'm going to just move that a little bit to match it up there. Okay. Then they walked back towards their starting point at a slower pace than they started. So when I draw this next line here, we're walking back, so I've got to go back downwards, but it says at a slower pace. So if I were to do it like that, that's probably about the same pace, because it's just, it's basically a reflection of the first line. But if it's a slower pace, that means the time is going to be longer to go that same distance. So it needs to be less steep. And it doesn't say they go all the way back. They don't get back quite to the beginning. So I'm going to make it something like that. And again, I just need to move this a little bit so it matches up well. And then, so we've done constant speed, stop for a break, walk back to the starting point at a slower pace. Close to the end of the hike, they walked at a constant speed again that was faster than their initial pace. So now we need to make it, this last line, steeper than the original line, okay? So if I don't want to do it like this, because that's the same as before, and I need to make it steeper than the original, okay? And again, I'm going to move it. So if I were to compare that over here as a reflection, you can tell it's steeper than the original. And you can make it a little bit more obvious, but you don't want to, say you did like this, a vertical line, that doesn't make sense. That means you can basically sort of time travel or whatever. You can snap your fingers and get there, and that's not real life. So you want to make it just a little bit steeper. So maybe they're kind of running back. So draw a graph that describes the distance they are from the starting point over time. And so it's already labeled, so we're good. Okay, the axes are labeled. We're not told any values, so we can't draw a scale. All right, and I just noticed here, I'm going to just make that go right to the 0, 0. All right. Okay, that's question 2. Question 3, you're matching up. So it says select the graph below that describes each situation the best. So what is that? 6 graphs, and we've got 6 explanations. And it doesn't say, they'll all match up. There's no extra, and it doesn't say there'll be repeats or anything. So let's read the situation. Probably best to do that first. So the first one, the temperature of the water in a bathtub is related to the number of minutes that have passed since you filled the tub. So think about it. When you fill the tub up, usually fill it with some warmer water because you want to have a bath. And so the temperature will decrease. Okay, so notice how it's not going to be the first one because that's sort of increasing. We call that a step graph. This is decreasing, so maybe it's that one. This is increasing, so no. This is changing, increasing and then decreasing, so that doesn't make sense. This is decreasing, so it could be that one, and this is increasing, so not that. So within these, we want to think about your bathtub. If you've had a bath, or you put anything that's hotter on, like say you've heated up a cup of coffee or tea and you put it on your counter, that tea is never going to get colder than room temperature. Your bathtub's never going to get, the water's never going to get colder than room temperature. So this is implying that it gets to a certain point at a constant rate. What you'll also find here with this curved one is it decreases quite quickly and then it basically approaches room temperature. Okay, it gets really close. So we call what this line is here, kind of, it's not a great line, but let me do this. Just give me a sec. So if I do this dotted line, it's called an asymptote, and you'll learn about it as we go through math. It's a line that a graph will approach but never touch, and that's really what happens to water. Okay, doesn't decrease at a constant rate. So that's going to be E. Right? So that's going to be E. Next one, the amount of gasoline remaining in a car's gas tank is related to how long it has been driven at a constant speed. So again, the amount of gas remaining, so this is kind of like the one we talked about above, how long it's been driven. So it's decreasing as well. So remember, the only decreasing ones were these B and E, and it says at a constant speed. So that means the decrease in the volume will be constant as well. So that's going to be B. Then the next one, the altitude of an airplane traveling from Calgary to Vancouver is related to the time in the air. So think about going in a plane. You start in Calgary, you go up in the air, you fly at a pretty constant altitude. I mean, it changes obviously, but on average, constant. And then you come back down and land. So we need something that's going up and then coming back down. Well, the only one is D here. Now, is that really what's going to be happening? Normally when you take off, it's going to be more curved. So really probably something like that. And going up, and then this might change, you know, if there's turbulence, they go up or whatever, but then it has to come back down, and again, a little bit levels off at the bottom, but that's an approximation. Okay, so that's the closest one of these 6. Cost of parking at the airport parking garage is related to the number of hours parked. So this is similar to a lot of places. Pay by the hour. It could be paid by the 15 minutes or half an hour or whatever, but parking is at the garage is usually by the hour, airport. And so if you, so you have to pay, it's quite expensive, I can't remember, but you have to pay like, let's say $5 for 1 hour. And you could say 15 minutes, 30 minutes, 42 minutes, 51.3 minutes. but it's still going to cost you that $5. So that's a case where we have a choice, really in this case, by A and C. F is not, because that's saying that you would pay for every minute or part of a minute, because that's joined up. And we've already talked about discrete and continuous. That's continuous. Parking fees are usually discrete. So when we look at, I shouldn't really circle that one yet. I'll put question marks. So here, this is saying for 1 hour, you pay a certain amount. For 2 hours, you pay a certain amount. But you can't stay for 1.5 because it's not joined up. This is saying, okay, let's say it's 1 hour there. Then you pay that amount and you can stay for the whole 1 hour. And then you can stay any part of that 1 hour. And then say this is 2 hours. So if you stay for 1.5 hours, you're paying for the 2 hours, okay? Because there's an amount there. So this is, this represents cost of parking the best out of all of these. So that's A, okay? And what we call this is a step function, because really it kind of looks like steps. Keep going up on this set of steps. And more specifically, it's a piecewise function. So there's different pieces. So it's also piecewise function. So we have 3 different pieces in that each have a different equation for those. Remember, the open circle means it doesn't touch 1 hour. So I actually, for parking, probably would have it more like open circle here and closed circle here, right? Because that's saying you could park up to 1 hour, and then for anything more than 1 hour, up to 2, you would pay. So again, this is the closest representation that's given. It might not be exactly what it is. Next one, the cost of a family flying to Vancouver is related to the number of people in the family. Well, you can't have part of a person, so you know it has to be discrete, right? And so the only one left is C. So for 1 person, it costs $500. For 2 people, it costs $1,000. That kind of thing, okay? So that makes sense for C. And the amount of water in a small swimming pool is related to how long the water has been running in. And so by default, only F is left. And so this is providing that you're pouring the water from the hose at a constant rate. So you turn it on, it doesn't change. And then this is saying this is for a pool. Once it gets full, then obviously that's going to level off. So this is when the amount of water. So this is when the volume is maximum volume here, right? Because then it would actually, the volume would level off and all the extra water would go outside, so you wouldn't really be measuring the volume in the pool. So that would be F. Okay. And next, the graphs below show how much it costs to purchase food items. So the first one is continuous. So here's the quantity, here's the cost. This one here is discrete. So you can see your separated dots there, quantity and cost. And it says, give an example of a food item that could be represented by each graph and explain why each example fits the particular graph. So you want to think about what you buy at a grocery store that you pay per item and what you pay for part of an item. Well, you can't usually pay for part of an item, but you can if you go to the deli department or the meat department, then you often buy, you're charged by the kilogram or by the pound, and you can buy 1.23 kilograms or 1.5 pounds. So no matter what the quantity is, between there, you can buy as much as you want. So that would be a case of a continuous. So this would be something like deli meat. Okay, so you can buy 1.21 kilograms. That's a lot of deli meat, but you can buy decimal amount of deli meat, or cheese, or as I said, beef, chicken, anything that's sold. I mean, usually those are in packages, so it's already telling you what you're getting. At a deli counter, you kind of tell them what you want, okay? And then quantity would be like cans of soup, something like that. Okay, 1 can of soup, 0 cans would cost $0. 1 can of soup would cost $1. 2 cans would be $2. Now, that doesn't take into account any sales for purchasing a certain number, but that would be an example. Okay, so you can buy this, so that's part of a kilogram here, and this is only whole cans. Okay, and that's it.